Hi, I'm Yu. Today I'm going to present a joint work with Rahul, Anup, Sarah, Rachel, and Ali. The title of our work is CrawLabel, Computing Natural Language Labels for UI Test Cases. Before I go into the technical details, I'll talk about the background and motivations. Testing is important and prevalent. There are ongoing efforts to make tests more comprehensible, including creating meaningful test case names and summarizing or documenting test cases. Today, we mainly focus on UI testing. End-to-end UI testing is widely used in industry to check whether the user interface and the system behind it behave correctly. UI testing exercises the application through user interface in the same way an end user navigates the application. A UI test consists of actions performed on the UI of the program, often via APIs of a testing framework such as Selenium. For example, here is a website about a pet store named J-Pet Store. On the left, state 1 represents a welcome page. After the user clicks enter the store, the page jumps to state 2 on the right. We can write a UI test to check if the transition is correct. To write a UI test, we need to locate the elements. The elements in the user interface is represented in a structure named DOM. For example, here is the HTML and DOM for state 1. The green box shows the DOM of the link enter the store, which has attribute href. The black box, which surrounds the green box, is the context of the link enter the store. It represents the largest subDOM that contains only one clickable. On the bottom, it is the XPath for the link enter the store, which can be used to identify and navigate nodes. Here, we show an example of UI test case with code. The elements are located by XPath. On the left, it is a path of state transitions from state 1 to state 4. Start with state 1, the link enter the store is clicked. The web page navigates to state 2. And then keyword bulldog is searched. The web page navigates to state 3. Then return to main menu is clicked. The web page navigates back to state 2. And in the end, the button fish in state 2 is clicked, and the web page navigates to state 4. If we write this testing process into code, which we can see on the right, then the test case that uses XPath is not readable. Also, UI tests are hard to maintain as they are fragile and can break in response to minor changes to the UI. Such test breakages require costly human effort in practice, so UI testing comprehension is very important. Previous work on test comprehension mainly focuses on unit test, which checks the correctness of function. However, UI testing more focuses on the interaction between elements. So if we add comments to these click operations, the tests will be more readable than before. Thus, the goal of our work is to generate readable labels for the clickables and the states used in UI tests. This is an overview of our approach for label generation. Before I introduce the overview graph, I'll first introduce Crawljax. Our technique is based on this tool, which automatically crawls and tests modern web applications. It identifies and extracts clickable elements and states by crawling the web page. We can see the state flow graph on the right, constructed by Crawljax. Nodes represent the abstract UI states. Edges represent the events that cause state transitions between states. The node and the directed edges construct the path. Passes that start from the first state can represent the test sequence. Back to our technique, once a user generates passes using Crawljax, we pre-process the clickables in the passes to extract the DOM and context of each clickable. Then, depending on whether we have training data for the testing framework being used, We offer two different but related solutions to generate labels for tests. If framework exists, the user can run the supervised approach to generate labels from the clickables. After we extract training data, we use heuristic and keyword to extract label. However, if the framework is not present, the user can choose the unsupervised approach to generate the labels. We aim to extract the most probable verb and the most probable noun and combine them to form a keyword. And in the following, we provide the details of the supervised and the unsupervised approaches. For supervised approach, first, we choose some applications with different frameworks as training data, as shown in the table on the right. The frameworks include jQuery, UIKit, AngularJS, React, and Ember.js. Because we do not have the right label, which is the correct keyword for our dataset, we manually label the keyword for each clickable. After doing that, we count how many times each attribute's value contains the keywords, and the result is shown in this heat map. We sort a frequent attribute as an attribute list. The attributes are shown on the right side of the heat map. We can see that text and href are the most frequent attributes, and we name finding keyword from sorted attributes as a heuristic rule. However, there exist challenges. The first challenge is that frequent attribute does not equal to meaningful attribute, and the value of most frequent attribute may contain meaningless word. So we added preprocessing step, including tokenizing the value to generate tokens, lemmatizing the tokens, removing stop word tokens, and removing non-English tokens. The second challenge is that the clickable may not have attribute in our trained attribute list. When this happens, we will use the outputs of an existing tool keyword as a label. Keyword is a keyword extracting technique based on popular BERT technique. It has 3 steps for extracting keywords from a set of documents. In the first step, it creates candidate keywords or phrases in terms of n-gram from a document. N-grams represent the sequence of word representation in a document. In the second step, it creates a BERT-based embedded representation for documents and the candidate keywords or phrases. And in the third step, it finds the candidates that are most similar to documents using the cosine similarity. However, the limitation for the first approach is that an application that uses a novel framework may contain different domain knowledge from the frameworks used for training, so that the trained attribute list does not apply to the new framework. So here we propose the unsupervised approach. This approach extracts keywords, the combination of verb and noun, that might represent an action invoked and the target of the action. And here we use linked fish as an example. It contains the attribute href and a subdom image. According to our solution 1, the first matched attribute of the attribute list is href. After applying the heuristic rule and preprocessing, the keyword is category ID. However, this keyword lacks action verb. What we expect to get is view category. The goal of our second approach is to extract the most probable verb and noun. We first conducted post-tag analysis, which marks part of speech to each word of the clickable. Because DOM is different from natural language, in each clickable, different values for different attributes may not consist into a complete sentence. We did post-tag analysis to each attribute's value instead of to the whole clickable. And on the right is the past result of previous example fish. And in this tree structure, leaf nodes represent word and the non-leaf node represent part of speech, such as NN, which represents noun, and NP, which represents noun phrase. After that, we apply probabilistic context-free grammar, PCFG, which extends the context-free grammars by assigning a probability to each production rule. A PCFG is represented by a finite set of non-terminal symbols, a finite set of terminal symbols, a finite set of production rules, and a conditional probability of choosing a production rule. And on the right is a past result of PCFG from post-tag analysis result. We can see that the probability of category with a parent noun is 0.0927, and the probability of noun with a parent of noun phrase is 0.2545. After we get the PCFG, we extract the verb with the highest probability and the noun with the highest probability. When there is no verb recognized by the post-tag analysis tool, we use VerbNet, which is a large domain-independent verb dictionary, to match verbs. If VerbNet still cannot detect the verb, we will make use of the context of clickable to find the verb. This figure presents an overview of the workflow implemented in CrawLabel, which takes as input the URL of the web application under test and generates labeled UI test cases. CrawLabel first invokes Crawljax. Then, the label generator analyzes the generated tests to infer natural language labels for test steps. The previous two solutions are implemented into label generator. And then, Crawljax labeling plugin combines the tests and label, and outputs the labeled UI test. To evaluate our tool, we propose the following research question. Are supervised and unsupervised approaches effective in computing labels for UI test cases? We use certain applications that have been used in prior work on UI testing. As mentioned before, the projects with different frameworks are used as training set. When multiple applications have the same framework, one application is randomly selected. That is to say, for example, Timeshift and PPMA both use jQuery, but Timeshift is randomly selected into the training set. And the remaining 8 applications serve as the evaluation set. To get the test cases, we use Crawljax to crawl these 13 projects. In the table, number of passes represent the number of passes crawled by Crawljax during the exploration, which equals to the number of generated test cases. Number of states represent the number of abstract UI states. Number of edges represent the number of clickables that cause state transitions. Number of URLs represents the number of unique URLs. And the last column shows whether Crawljax completed its run within the 1 hour limit. If it completed, the table shows exhausted. Otherwise, the table shows maximum time passed, which means the Crawljax terminated after reaching the time limit. We have two baselines. One is to simply applying preprocessing to clickable. The other is to directly send the clickable as input to keyboard and choose the most probable keyword as label. We have the following metrics. The manually assigned labels are considered as the reference text or the ground truth. These measures are computed by comparing the model output with the reference text. And here is how we calculate the precision, recall, and F1. And for the RAUJ is a set of metrics widely used in measuring accuracy of summarization. RAUJ N measures the number of matching n-grams between the model output and the reference text. RAUJ L measures the longest common subsequence between the model output and the reference text. For RAUJ 2, if the manual label contains only one word, we use the value of route 1 as route 2 as the smoothing method. The last matrix, the edit similarity, when we calculate it, we use the Levenstein distance, which is a string metric for measuring the smallest number of edit operations required to transform one string to another. The character level edit similarity is calculated as 1 minus normalized Levenstein distance. The higher the edit similarity, the more similar the model output is to the reference text. This table shows the effectiveness scores achieved by the techniques on average. The highest score is highlighted in boldface. We find that the supervised approach performs better than the baselines and the unsupervised approach in terms of precision, F1 score, and edit similarity. The preprocessed baseline outperforms other approaches in terms of recall. This is expected because it retains all the words in the clickable except the stop words. To further compare the results on each application, we make the following 4 box plots. For the metric f at 1, in terms of the median value, the unsupervised approach performs better than or the same as the baseline techniques for 6 applications. The supervised approach performs better than or the other approaches for 6 applications. For metrics f at 2, supervised and unsupervised perform better than or the same as baselines for 6 applications and 3 applications respectively. For metrics f at L, supervised and unsupervised perform better than or the same as baselines for 7 applications and 5 applications respectively. In terms of edit similarity, supervised and unsupervised approaches perform better than or the same as baselines for 6 applications and 3 applications respectively. Here is our discussion part. First is the importance of clickable elements. The success of the supervised approach reveals that the clickable element of a UI test step contains attributes that carry meaningful information about its function. Some attributes, such as text and href, tend to contain more relevant information than other attributes. This is evident by the high average precision, recall, and F1 score that the supervised approach achieves. Second, differencing the source and target states. Differences between the source and target states of a clickable and focusing on the state transformation triggered by the clickable could provide useful information about the semantics of the action performed. However, during our calculation, if we simply remove the same part between the source and target states, we found that what left is too much and contains much noise, so further investigation of the usefulness of state differencing for labeling would be worthwhile. Third, the competitiveness of the unsupervised approach. The results on the unsupervised approach are quite promising, considering that first, it does not require training data and prior familiarity with the application under test, and second, its performance according to our evaluation is only slightly less than that of the supervised approach. Last but not least, we discuss about the usefulness of analyzing the context of clickable. After disabling context analysis, for unsupervised approach, we found that the average value for these matrices all reduced by a large percentage. So to conclude, we introduce an approach for generating natural language labels for UI test cases. We propose 2 techniques for selecting the DOM attributes. The unsupervised technique proved competitive, though the supervised one performed slightly better. In most cases, analyzing only the clickable element for a test step is sufficient to generate a meaningful label. And in the future, we can conduct a user study that investigates the impact of our generated test step labels.